Welcome back, everybody, for another deep dive. You guys have sent in some seriously fascinating excerpts on quantum physics this time around. We're going to be talking about some really wild concepts like fractional charges and the role of gravity in quantum measurement, even the possibility that electrons, well, they might not be as fundamental as we thought.
Yeah, what's really interesting to me is that a lot of these excerpts that you sent in, they all touch on this concept of emergence. The idea that these really complex phenomena that we observe, they can actually just arise from the interaction of these much simpler components. It really kind of challenges how we think about the universe, like
Yeah.
what's truly fundamental.
Yeah, for sure. Okay, so let's dive right into it. One of the first things that jumped out at me when I was reading through this was how temperature affects these quantum systems. And these excerpts suggest that there are some pretty dramatic changes that happen at these really, really extreme temperatures.
Oh yeah, absolutely. Temperature, I mean, it is a crucial factor in how these quantum systems actually behave. Um, you know, at temperatures close to absolute zero, like really, really cold, we see things like superconductivity,
Hmm.
where electrons can just flow with zero resistance. But then on the other hand, when you crank up the heat at extremely high temperatures, the stability of these quantum singularities,
Mm.
well, it gets affected. And we might even see these, like whole new particles or
Yeah.
charged states that emerge.
So it's like, I don't know, like a cosmic dance floor or something. The temperature is setting the tempo, and depending on how much heat there is, you get, different moves, different partners, maybe even a whole new genre of music.
Yeah, I like that. That's a great way to put it. Yeah. And the excerpts that you sent also, they mentioned how these temperature-driven phase transitions, they can cause these like really fundamental shifts
The
and
electric.
charge interactions
Yeah.
and electromagnetic forces.
Right.
Think about the Curie temperature for these ferromagnetic materials.
Yeah.
Above that specific temperature, well, they completely lose their magnetism.
Oh, right, right, right. And that's because the increased thermal energy, it disrupts the alignment of their magnetic moments.
Exactly. Yeah, that's it. And it really highlights how sensitive these quantum systems are to changes in temperature. And, it's also why temperature control is so important for a lot of the technologies that, you probably use every day. Like think about your phone
Mm-hmm.
or your computer. The semiconductors in those devices, I mean, they rely on really precise temperature regulation for them to function correctly.
Oh, wow. Okay, so that's a really cool connection to our everyday lives. I like that. Okay, so one of the most, I don't know, mind-bending concepts in these excerpts is this suggestion that electrons, electrons, they might actually be composite structures.
Yeah, it's a really interesting idea. It really challenges the way that we've traditionally thought about electrons as these like point-like particles. The excerpts that you sent, they propose that electrons could actually just emerge from the interactions of these quantum singularities, charge
Yeah.
and momentum.
So instead of it being like this fundamental building block, it's more like a complex machine, with
Right.
all these moving parts, all working together to produce the properties that we observe.
Yeah, that's a good way to think about it, if this is true. I mean, it could revolutionize our understanding of how electrons behave
Hmm.
and interact with each other. For example, their mass, their spin, their charge, all of that could just be consequences of this underlying dynamics. It would change things.
And speaking of charge, the excerpts mention this thing called fractional charges. I mean, is that even possible? I always learn that charges, they come in these whole numbers.
Yeah, it definitely challenges our conventional understanding. But your excerpts, they propose this new emergent particle with charges of plus or minus zero point 0.5,
Hmm.
which is pretty wild.
Yeah, it's a really bold idea. It suggests that charge might actually exist on a spectrum rather than in these like discrete steps.
So instead of having like only whole notes in music, we could have half notes and quarter notes,
Yeah.
creating this whole new level of complexity and nuance. Exactly. Yeah. And it opens up all these possibilities for like much more granular charge interactions.
Yeah.
And it could potentially explain some phenomena that just don't fit neatly into our current models. For example, there are these exotic states of matter that might exhibit these fractional charges.
Okay, this is blowing my mind a little bit. We're talking about potentially rewriting the rules of electromagnetism.
Yeah. It's pretty exciting to think about. It's a great example of how these excerpts can really make us reconsider some of our assumptions about the universe.
Yeah, for sure. Another concept that really jumped out at me was this idea of gravity playing a role in quantum measurement. The excerpts even mention this modified equation that links these two seemingly separate realms, which I thought was really interesting.
Yeah. This ties into one of the biggest mysteries in quantum physics, really. It's called the measurement problem. Essentially, it's, How does a quantum system that's in a superposition of states, like, think about Schrodinger's cat being both alive and dead at the same time, how does it collapse into a single definite state when it's observed?
Right. It's like the act of observation somehow forces the universe to make a choice, which is really weird.
Yeah, exactly. And this modified equation, it suggests that gravity might actually be the missing piece of the puzzle. It proposes that the interaction between quantum fields and the curvature of space-time, which is, influenced by gravity, it could play a role in triggering this wave function collapse.
So gravity is like the cosmic referee, determining when a quantum possibility actually becomes a concrete reality.
In a way, yeah. And it connects to Roger Penrose's objective reduction theory, which suggests that gravitational influence, it might cause wave function collapse. When the energy difference between these superimposed states, it becomes significant enough.
Okay, my head's spinning a little bit, but it sounds like we're talking about a potential revolution in our understanding of both gravity and quantum mechanics at the same time.
Yeah, it's definitely a profound idea, and it raises even more questions about how gravity operates, at this quantum level, which we just don't fully understand yet.
All right, so we've talked about the impact of temperature, the possibility of composite electrons, fractional charges, and gravity's role in quantum measurement. What other mind-bending concepts are lurking in these excerpts? I'm ready for more.
One of the things that really stood out to me was this suggestion that even electrons and ions and charges, things we think of as being so fundamental, might not actually be fundamental entities. Instead, they might be, like mediative emergent properties. It's really taken this idea of emergence to a whole new level.
Oh, hold on. Even charge could be emergent. I mean,
Yeah.
that's a pretty big departure from how we usually think about charge, right? What exactly does that even mean?
Well, it suggests that instead of being, is an inherent property of particles, charge could actually be a consequence of the complex interplay of, these quantum singularity dynamics. Imagine, these quantum singularities
Yeah.
as these tiny swirling vortices of energy.
Okay. I'm trying to picture that.
Yeah. Now imagine these vortices interacting with each other, through their surrounding fields, the way they exchange energy and momentum. Well, it could give rise to what we perceive as charge.
Oh, wow. Okay, so instead of charge being like the static property, it's more like a verb, like a dynamic process that arises from these interactions.
Yeah, that's a great way to put it. Exactly.
Right.
And these emergent particles, like electrons and ions, they would act as mediators between these quantum singularities and the larger scale electromagnetic fields that, we observe.
That's a pretty wild concept. It makes you wonder what else might be emergent, that we currently consider fundamental.
Okay.
Yeah.
Speaking of mind-blowing ideas, the excerpts also touch on the potential for these new forms of electromagnetic radiation arising from the existence of particles with fractional charges. That one was really interesting to me.
Yeah, this is a particularly intriguing consequence of the fractional charges. If particles can have charges that are not, simple multiples of the electron's charge, it opens up the possibility of these electromagnetic interactions that we've never even observed before.
Oh, so instead of just having the familiar spectrum of radio waves, microwaves, visible light, and all that, we could have these entirely new bands of electromagnetic radiation. It's like discovering a whole new set of colors that we never knew existed. It is, yeah. That's a great analogy. And these new forms of radiation, they could have really profound implications. They might interact with matter in these completely novel ways, leading to new technologies, maybe even new understandings of the universe. For example, they could give us new tools for probing the structure of matter, or maybe even detecting dark matter. Who knows?
Wow, that's amazing. Okay. It's like we're on the verge of discovering a whole new realm of physics. But before we get too carried away, let's shift gears a bit. One thing that really caught my eye was this interplay of temperature, water, and quantum singularities, particularly in the context of bioelectricity. That was really interesting to me.
Yeah, this is an area where, quantum effects might be playing a much bigger role than we traditionally thought. The excerpts that you sent, they point to this fascinating connection between water and these tiny, powerful quantum singularities.
Yeah, I mean, water is obviously essential for life, but I usually think of it as this pretty simple molecule. How does it tie into, this quantum realm?
Well, while it's true that its molecular structure is simple, water's behavior, it's surprisingly complex, especially at the quantum level. The network of hydrogen bonds, between water molecules, they could exhibit these quantum phenomena. like tunneling and coherence, for example, which, it could potentially influence processes like proton transport and even enzyme activity.
So even something as seemingly mundane as water might be harboring like quantum secrets.
Exactly, yeah. And the excerpts, they also mention this idea of water memory, which is, the possibility that water molecules can actually retain information about substances they've previously interacted with.
Oh, yeah, I've heard of that. But isn't that considered kind of like fringe science?
It's definitely a topic of debate. But the basic idea is that the structure of water, particularly the arrangement of its hydrogen bonds, could be subtly influenced by past interactions. And it kind of leaves behind this molecular imprint.
So like a fingerprint, left behind by a fleeting encounter.
Exactly. Now, how this relates to quantum singularities is still, very speculative. But some researchers, they propose that these tiny points of energy, they might interact with the electromagnetic fields that are associated with these water molecules. And it could potentially influence their behavior and even, their ability to retain information.
So it's like quantum singularities are whispering secrets to water molecules, shaping their structure and influencing the, delicate dance of life itself.
Yeah, that's a very poetic way to put it. I like that. And this brings us back to bioelectricity. The excerpts suggest that quantum effects, they might actually play a significant role in the way that, these electrical signals are generated and transmitted within biological systems.
So we're not just talking about like, the flow of ions through channels, but something more profound is happening at the quantum level.
Precisely. Yeah. If quantum phenomena like, tunneling and entanglement are involved in the behavior of water and other biomolecules, well, it suggests that bioelectricity might be more than just a classical phenomenon, which is, kind of how we've traditionally thought about it.
Our bodies are running on quantum circuits. But how could such delicate quantum effects even survive? In the warm, messy environment of a living cell, wouldn't they just get disrupted?
That's a great question. And it's one that researchers are actively trying to answer. Some speculate that biomolecules like proteins and DNA, they might act as like quantum antennas, maintaining coherence and facilitating quantum processes, even in the face of all this thermal noise. Others suggest that the highly structured environment, within cells, it might actually help protect these delicate quantum states. But we need more research to say for sure.
Yeah, that's really interesting. It's mind-boggling to think that like our thoughts and feelings and actions might be influenced by, quantum mechanics. Okay, speaking of mind-blowing, one of the excerpts mention the potential for harnessing quantum singularity for energy production, using concepts like quantum fission and fusion. What are those?
Yeah, the excerpts, they don't go into a ton of detail, but they seem to be suggesting that by like manipulating these incredibly dense points of energy, these quantum singularities, we might be able to induce processes analogous to nuclear fission and fusion, but on this like quantum scale.
So instead of splitting atoms or forcing them to fuse, we'd be manipulating these, tiny powerful points of like pure energy.
That's the implication.
Yeah.
And the energy released from that, it could be immense, potentially dwarfing anything that we can achieve with current nuclear technology. But of course, this is highly speculative. We're nowhere near having the technology to manipulate quantum singularities in this way.
Yeah, it sounds both incredibly exciting and a little terrifying, to be honest. We'd have to be extremely careful not to like unleash a quantum catastrophe.
Yeah, absolutely, yeah. Manipulating such powerful entities. It would require a level of understanding, precision, that, we haven't even begun to approach. It would be a whole new ballgame.
Okay, we've covered a lot of ground here. We've talked about emergent properties, fractional charges, bioelectricity, and even the possibility of, quantum energy production. Is there anything else in these excerpts that you think we should touch on?
There's one more concept from these excerpts that I think we should definitely talk about. It's probably the most mind-bending one of all, honestly. Yeah. A lot of these excerpts hint at this idea that even gravity itself might be an emergent phenomenon, which is kind of breaks your brain a little bit. What does that even mean? Gravity seems so fundamental to the universe, right?
I know, right? It's one of those things you just take for granted. Okay, so we're not talking about Newton's apple here or Einstein's curved space-time, right? Like what kind of deeper process could give rise to something as all-encompassing as gravity? It's kind of hard to wrap your head around.
Well, one of the leading theories out there, it's called entropic gravity. And it proposes that gravity, it actually just emerges from this tendency of systems
Mm.
to move towards
Yeah.
higher entropy, which is essentially a measure of, like disorder or randomness.
Wait, so you're saying there's a connection between gravity and the universe's tendency to, like, get messier over time?
Yeah, that's the basic idea. Imagine space-time as this like vast network of interconnected information. As systems evolve and their entropy increases, the information associated with those systems, it just like gets spread out
Hmm.
over a wider area.
Okay, I think I'm following you so
All
far.
right, so this spreading of information, it's thought to create a kind of entropic force that pulls things together. And that force is, well, that's what we experience as gravity.
Oh, wow. Okay. So gravity is like the universe's way of like tidying up information, even though it might seem messy to us, on a larger scale.
Yeah, that's one way to think about it. And it connects to this idea that information itself might actually be a fundamental aspect of reality, just as fundamental as, like, matter and energy.
Well, hold on. Information
Mm.
as a building block of the universe. That's a big idea. But
Yeah.
where do these quantum singularities fit into all of this? I mean, they seem to be all about like concentrated information, not spread out information.
That's a great point. And if gravity is indeed, this emergent property of information spreading out,
Right.
then quantum singularities, with their incredible, like dense concentration of information,
Yeah.
well, they would have a huge gravitational pull.
It's like they're ultimate information hoarders, warping space-time around them with their massive gravitational influence.
Exactly. And the more information a quantum singularity contains, the stronger its gravitational pull would be. It's kind of a cool thought.
So these quantum singularities, these tiny points of like extreme information density, they could be the ultimate source of gravity.
It's a fascinating possibility.
Yeah.
And it raises the question, if we could somehow access and understand the information that's contained within these singularities, could we unlock the secrets of gravity itself?
Yeah.
It makes you wonder.
I mean, that's a pretty mind-blowing thought. And we've been talking about emergent properties all throughout this deep dive. It's incredible to think that so many things that we always thought were fundamental, like electrons, charge, even gravity, might actually emerge from something even more fundamental, something related to like the very fabric of space-time and the nature of information.
It really is. It's a paradigm shift in how we view the universe. It suggests that reality, it might be more about information
Mm-hmm.
and its interactions than about these like particles and forces that, we traditionally study in physics.
Well, this has been an incredible deep dive. We've explored so many fascinating concepts, temperature's impact on quantum systems, the possibility of composite electrons and fractional charges, gravity's role in quantum measurement, the emergence of charge, and even gravity itself, the potential for new forms of electromagnetic radiation, the interplay of water and quantum singularities in bioelectricity, and even the idea of information, as a fundamental building block of reality. It's pretty wild.
It's amazing how these like seemingly disparate ideas are all interconnected.
Yeah.
It really points toward, I think, a much deeper understanding of the universe that we're just starting to like scratch the surface of.
It really makes you appreciate the mystery
Yeah,
and the wonder of the quantum realm. There's so much we don't know.
absolutely. And I think it underscores the importance of staying curious, questioning our assumptions
Mm.
and being open to new ideas. I think that's what makes science so exciting.
Couldn't have said it better myself. And thank you to all of you for joining us on this deep dive into the quantum world. We hope you found it as thought-provoking and mind-bending as we did.
Yeah, remember, the journey of discovery never ends. Keep exploring, keep asking those questions, and keep pushing the boundaries of knowledge. We'll see you next time for another deep dive.